I will talk about topology and mostly in out of equilibrium ideas. But before starting, let me first. So this will be a more tutorial-like session. So I will be giving a lot of introduction and background information, but I will be also showing you some new research. And this before starting that, so this involves several active collaborations over the years. So I've had the pleasure of working on the theory side, which particularly relevant to the talks and papers ideas that I'm going to mention today. It's worth mentioning Nigel, Robert, Adrian from Cambridge, Nathan from Brussels, Andre Berlin now, and Babak from Indiana. I will be showing some results from my master's students, particularly Cameron and Miguel. And I've also had the great pleasure to take these theory ideas and then put them into a test in experimental settings. So in relevance to this talk, these papers involved collaborations with Emmanuel and Monica in Munich and Klaus and Christoph in Hamburg. So, okay, so this is the outlook. So I will be talking today and tomorrow morning. So I want to introduce you topology and then like these new topological ideas. And particularly, so if I need to identify a crown jewel of this talk, I would say that this multi-gap topologies, Euler topologies that have been arising in the last 2 or 3 years, and but under out of equilibrium conditions, for example, under periodically driven systems, we have been just like discovering new topological phases for this. So. But of course, to make it more pedagogical, so I want to give you a background information on what is topology. So this will involve like single gap topology, what's been known so far. So these are things like Chern numbers. So I will first introduce you this. So what is topology, what is Chern number, and there can be a one can make several different introduction coming from different angles. You can just like talk about K theory, what is the more mathematical way or a more physicist way. I want to give you a more geometrical view that like you can visualize and then understand these ideas, and then like express like how maybe also a little bit of tangent, like how these ideas just like extend the complexity of the geometry extent. And then I want to tell you these within the settings of these single gap topologies and Chern number, when I include periodic driving, in the spirit of this workshop. So what kind of new topologies that like we can get? And then after that, I want to go to new types of topologies, Euler class. So I will probably not have time. So this in the slide that I must have just deleted, I don't know, before coming here, I don't remember doing that. But so I want to tell you about these anomalous Euler insulators, like that come like combining this and then with this Floquet driving. So why I'm doing this is that, so we have these topological ideas that emerge in equilibrium. We like topology, it's quantized, robust. But when we go to out of equilibrium, this allows us to discover new kind of phases, new topological invariants, new responses, and new kind of connections between different topological invariants. And on top of it, I mean, life is dynamic, just like eventually if you want to implement something, this is going to be some out of equilibrium setting. So in this part tomorrow, so I want to tell you about some other kind of out of equilibrium setting, quenches, that like you suddenly change the Hamiltonian. So today it will introduce, today will involve some introduction on topology and Floquet topology. Tomorrow I will tell you about quaternions and then this new kind of topological invariance linking number that we have been seeing on the different phases involving these out of equilibrium quench dynamics. So with that, let me go back. So, and in terms of the setting, so the setting that you can imagine, like study these questions are quantum simulators. Why? Because I mean, so we all want to solves complex quantum systems, but this is too complicated to do in many cases. So we can either involve some numerical approximations, which are proven to be extremely powerful, but they usually work in certain settings under certain restricted conditions, or we follow the idea of Feynman, which involves just like simulating one complex system by using another one. So for the sake of also, I mean, for the younger generation among us here, so what this means is that, so we are interested in some Hamiltonian, and we cannot solve this thing numerically in our system, but what we can do maybe is that preparing this Hamiltonian in the lab by using much more controllable other objects. Okay, so we prepare this Hamiltonian, and then what? What we can also do is that we can prepare a ground state wave function, for example, and expose that state, quantum mechanical state, to this Hamiltonian. So this state is going to evolve under this Hamiltonian, showing some responses and stuff, and we can probe that response, which will tell us something about these Hamiltonian. So in this idea of quantum simulation, so you are in principle engineering the individual elements of the Hamiltonian. Particle types can be controlled, lattice shapes can be controlled, optical lattices, interactions can be controlled. You can just like go to different dimensions. So in principle, so world becomes your oyster. And so these ideas allowed to, just like extend several different fields, of course. So I'm going to focus on condensed matter and then several specific subsets here. But I want to show you how these topological ideas, how they actually occur in the experiment. So I will also show you some some experimental results that hopefully that will make you believe me that like, oh, there is a linking, oh, there is some topological state there. So these are very good for proof of principle studies. I will put it to check here. That's and then new probes. Yes, we can go new probes. We can study new regimes like these periodic-driven or quench dynamics, and then discover new phenomena. So with this, let me start topology. So one of the first instances that topology has entered our lives in physics is through the integer quantum Hall effect. When Klaus von Klitzig took a two-dimensional electron gas, cooled it down to cold enough temperatures under a perpendicular magnetic field, they observed these steps for the transverse conductivity as a function of the magnetic field. So this means that like if I change the magnetic field a little bit, the quantized conductance, transverse conductance, stays flat. If I change the temperature, it stays same until it jumps to a different value. And the connection of these steps, these discrete steps, to the Chern number, underlying Chern number, and genus Gauss-Bonnet theorem has been developed afterwards. And then this has been, extended to also settings that doesn't require a magnetic field later, but held in. So in principle, this is what topology is about. So you have some quantized response. You can do some changes to your system, like deform the system, and then your observable doesn't change. And this is the kind of the view that I want to give you by giving this geometrical approach. And so here, I want to just like put some, exclamation marks. So this is called anomalous topological insulator. And then anomalous in the sense that, so you can just like see people calling several different phases anomalous, and then this might become confusing at some point. So this is anomalous in the sense that there is no net magnetic field. There is some local magnetic field. You have some flux within the unit cell, but there is no net magnetic field and anomalous in that sense. You just need to break time reversal symmetry. And when I say anomalous Floquet topological insulators, so they are anomalous because there's an additional gap. So they are anomalous for different reasons. And from this point on, when I call anomalous, I mean anomalous Floquet topological insulators, and I will also introduce that. So in a sense, so there's something called bulk edge correspondence, which means that if I have a Chern number 3, 1. So this Chern number gives me the number of edge states if I have a finite system. In a classical way, you can think about it under the magnetic field. So these particles, electrons, are doing cyclotron motion within the bulk, but then in the edge, they need to follow this chiral motion, and a number of those channels are given set by the Chern number, and then these are the current carriers giving me the quantized response. Okay, so but how does this come about? So now, imagine that I have some two-band model, any Hamiltonian in a two-dimensional system. So I have Kx, Ky lattice model. I can just like express this by using Pauli matrices. And so Brillouin zone is a torus, okay? And then I want to take one of the eigenstates, say the lowest eigenstate of this Hamiltonian, psi. And then if I adiabatically transport this wave function around the edge of the Brillouin zone, because Brillouin zone is a closed surface, torus, this state must come back to itself. But it can also take some phase, e to power I 2 pi. So this is free. And then this is exactly what Chern number is. How does this adiabatic transport work? So let me, instead of just like going all around, let me just take random 4 points, okay? And then I have two wave functions here. The phase between these wave functions here at point 1 and point 2, K1, K1 are just like, I just overlap. And then I'm not interested in the magnitude, so I divide by the norm. So there can be some phase between these wave functions. So it will be given by the imaginary times log of this thing here. So now let's follow a closed path. Okay, so delta phi 1, 2, 2, 3, 3, 4. So this I will just like sum since it's with the exponential, so it will be just like multiplication of these logs, imaginary times logs. So I have psi k1, bra, ket, k2, and then from the next point I'll come, and then that will be also divided by the norms, but norms don't matter for this discussion. So what I mean here is that, so what I'm trying to emphasize here is that at each point for these wave functions, normally there is a gauge degrees of freedom. So for each these k, I can put some random phase to it. But because these things, wave functions come in pairs, as bra and ket, this phase is not going to matter when I do a closed path. This psi 1 is going to cancel with the last one here. So it means that this phase that I can pick up when I go around a closed circuit, like as a path, is gauge invariant. So it must be observable. So now, instead of this discrete way, let me just do this in a closed, like continuous way. If I just like write this phase as a continuous phase for the like infinitely small path, so this phase is given by the derivative, just like how this wave function is changing along this thing, and this is exactly what we call a Berry connection. And if you take a curl of it, we have a Berry curvature. So this is very familiar from the electrodynamics. So it looks like a vector connection, and this looks like a magnetic field. So that's exactly what Berry curvature is. When I have it acts like a magnetic field in the Brillouin zone. When I go around it, if there is a flux, if there is a magnetic charge there, monopole sitting there, when I just like go around it, I'm going to pick up the flux that's coming out of it, and this is going to be quantized. Okay, so this is mathematically how this works, and there can be even nicer ways to visualize this. So now let me say that I have this lattice in the real space. So I have my Brillouin zone, but this edge is same with that edge, and this edge is same with that edge. So I have a torus. Okay, so I take again the eigenstate, this I was following, lowest eigenstate. So if I have now imagine that I start from a topologically trivial state. The Hamiltonian was a 2 by 2 Hamiltonian, right? So its eigenstate is 2 by 1 vector, so I can express this thing on block sphere. So if this state is topologically trivial, at each point in K, wave function can be all pointed at the same like north pole at each point. So this is a completely trivial state, completely boring, nothing's happening. So nothing is happening. So now somewhere in the Brillouin zone, I can start deforming this by changing the Hamiltonian. I can start deforming these wave functions. So now this state on the block sphere, on the Hilbert sphere, so this is my vector bundle, it's going to spread a little bit on the block sphere. So, but what you must be careful here about is that, so this thing here that I'm illustrating on the block sphere, this is not a piece of paper. A piece of paper is an open surface. Brilliant zone is a closed surface. So you should imagine this thing, something like a deflated balloon that you tie this thing. So it's a closed surface. And I'm stretching it a little bit, starting from the North Pole, but it must come back and close. Okay, so I can do this thing, keep doing it. Just I'm trying to cover the sphere, but Chern number is still 0. This is still a topologically trivial state because topology is all about smooth deformations that without doing any tearing or gluing, I can connect this state back to the completely trivial one. But at some point, if I just like puncture a hole to my balloon and then reconnect it around the sphere, so this is a topologically non-trivial change. And how does it look like in my vector bundle of the eigenstates? It looks like a Dirac cone because I was following this eigenstate, lowest eigenstate. If bands at some point, because I was deforming the Hamiltonian, right? If bands at some point touch, at that degenerate point, I cannot well define the eigenstates. I cannot find them. This is exactly what tearing is in the Hilbert space of the wave function. So when you listen to the talks of topology, you usually see oranges and donuts. What's the difference between an orange and donut? You must poke a hole. So this is how you poke a hole in the vector bundle in the Hilbert space of the eigenstate manifold. Okay. So by the way, if there's any so stop me. Okay. So if you have any questions, just let's start a discussion here. So now to make things a little bit more mathematical, so let me imagine this for this two-level system. And this is, I emphasize that this is the minimum state you require, because I was mentioning that like we have these single gap topologies. Single gap topologies require minimum embed, and then this will be important when I move to the more complex topologies. So any two-level state, I can express this two-level state by using two angles. So what I need is that, so it must be normalized. So I can distribute the probability as sine and cosine, but this is a complex quantum state. So they can also have some phase difference between them. And if I calculate the Bloch vector by sandwiching the Pauli matrices, this is going to point to some direction on the Bloch sphere. Okay, so this is the complete characterization of a two-level qubit. And if you just like take this description and calculate the Berry curvature, you would get this. This is a Jacobian on the sphere for the azimuthal angle phi and then cosine theta, the z-axis value on the Bloch sphere. And this is what we call a solid angle. So I was telling you that like this topology Chern number is the covering of the two sphere, which is mathematically expressed as pi 2 of S2. And then this is captured by this Jacobian. What's happening is that, so I have these wave functions in the Brillouin zone, okay? I can state from some point, for example, from the South Pole, okay? So I have now imagine that I have this Brillouin zone. I start from some random point, and at this point, my state is pointing to the South Pole. So now when I go immediately around it at these points, so if my Hamiltonian is continuous, in physics, we usually deal with these continuous Hamiltonian, they could be just like slightly deviating around that, but I can always find a unitary transformation. And these unitary transformations are going to be smooth in K as I go away to make that state point back to the South Pole where I start. So what I'm trying to do is that I'm trying to trivialize states everywhere in the Brillouin zone. So I can keep doing this for all the points on the Bloch sphere, except if at some point in the Brillouin zone, this way here, if my state is pointing to the North Pole, so I need to again rotate this back. I need to apply a pi rotation, but around which axis? I can rotate anywhere around the equator. So which means that this is discontinuous, right? I go there. So this rotation here is ill-defined, okay? And this is what, I mean, topology doesn't like these discontinuous changes. And this is how, this is the situation that tells me that like, oh, my Chern number is 1 here. I cannot find a smooth unitary transformation that trivializes the everywhere, my state in the Brillouin zone, okay? So it means that Chern number is 1 here. So this picture, this is powerful, okay? So, so now I want to, so So I mean, as I said, so Chern numbers, so these require minimum 2 levels. And then we have this very powerful visual aid of a Bloch sphere that like I can describe my state. I can show my Hamiltonian, depict my Hamiltonian on it. I can just like depict my states as Bloch states. For the rotations, time evolutions, these are just precession on the Bloch sphere. I mean, from the high energy to superconducting qubits. So this Bloch sphere picture is being employed in several disciplines, because in physics we like 2-level models, and then they are nice to understand. But now imagine that I go to a multi-level system. Okay, so in a similar way, for a 2-level system, I have SU2 algebra. Generators of SU2 algebra are polymatrices that I am very familiar with. And if I go to a multi-level system, I have Gell-Mann matrices that generate the algebra. So I can express any Hamiltonian, any Hermitian matrix can be fully expressed by the Gell-Mann matrices. I just ignore the identity, the overall phase shift. For any state, wave function can be again expressed on a Bloch hypersphere now. This can be catered to pure states or mixed states. So for mixed states, some people call this a Bloch ball. You may or may not like this, this name. So, but this is quite powerful. And this actually completely generalizes to any n-level quantum mechanical system. But now imagine that I have a 3-level state. Instead of a qubit, I have a qubit. I have 8 Gell-Mann matrices. So for my wave functions and Hamiltonian, I'm talking about, so now I want you to imagine a 7-sphere in 8 dimensions. So this is what's called a Bloch hypersphere. And these descriptions exist in math, in physics, but they are, I mean, it could be really powerful if they were intuitive, but they are hardly intuitive. And in terms of Chern number, for example, here I'm interested in topology. Chern number is formally given by pi2 of S2, even if when you have a multi-band level. But what is the S2 here? So this description, this understanding is completely lost when I go to n-level systems. So now I want to give you an intuitive understanding, intuitive picture for this general Bloch hypersphere. And beyond topology, this will be useful. So what can we do? So for a 3-level system, a qubit, so I need a quantum mechanical state, 3 levels. So I need 3 complex numbers. So this state, a qubit lives in C3, but in general, the overall phase doesn't matter. And this state is normalized if I'm interested in pure state. So there are 2 constraints. So for these 3 complex numbers or 6 real numbers, 2 constraints, this reduces to 4 independent number. This is what's called the CP2, the complex projective plane. So any 3-level quantum mechanical state is an element of CP2 here requires 4 independent parameters. And I can choose these 4 independent parameters to be angles, because they were really useful in the qubit case, right? And now, but I need to choose these angles in a really specific way. So these are the Gell-Mann matrices, 8 Gell-Mann matrices of the 3-level system. And my inspiration here is going to be that take these diagonal Gell-Mann matrices. So this state must be normalized, right? So let me distribute the probability between this element and these 2 elements here with a cosine theta. And within these 2, with another cosine sine var theta. So this is going to be squaring to 1. So it's normalized. But now this is a quantum mechanical state. So I must also put some phase difference. So I put some phase difference between this element and this element with a e to power I phi, and within this subset as var phi. Okay? So while distributing these angles, I treat this last element for the last diagonal Gell-Mann matrix, this element and this block as if some 2 entity. And then when I zoom in here, I have another 2-level, my usual sigma z. So if I follow this specific way dictated by the algebra, and if I calculate the Berry curvature separates into 2 Jacobians again, very nicely. And then remember that a sphere is described by a Jacobian. So I have some, for the first Jacobian, I have some azimuthal angle, the one that I put here, and some z-axis value, cosine theta. And then for the other Jacobian, I have this azimuthal angle, and then another value that's again between -1 and 1. So these, like the z-axis of an exterior sphere that is associated to this last Gell-Mann matrix. So for its poles, so if I take this one and sandwich between my states, lambda 8, so I have the 8 component of the coherence vector of my state on the below hypersphere. So its poles are where this thing takes maximum and minimal values. And then in a nested way, in a hierarchical way, because this value S3 here, or the lambda 3 matrix, so it also depends on theta k, so that's why they are nested. There is another interior sphere. So what I'm doing is that I have a Berry curvature for this state, n-level state, and then I can express this Berry curvature as the solid angle, how much of this exterior sphere I cover, and then how much of the interior sphere I couple. They very nicely decouple. And if I do this thing, so yes, which part? Yeah, okay, so motivation. So are you clear with that? I need, could I convince you that I need 4 parameters? Okay, so this 4 parameters, so I am just like distributing them in a way that like that already satisfies the normalization. Okay, so if I just like square this thing, the phases don't matter. So within this subset, cosine var theta, sine var theta is going to give me 1. And then I will end up having cosine square theta, sine square theta 1. So this is normalized. Because this theta has an azimuthal polar angle character, so this sine theta can take any value, right? Between 0 and 1. So then I just like choose this is okay. So this is a complete description of a 3-level qubit state in the most generic way, okay? 3-level state. But you could also choose this thing some other way. You could actually just like write sine. You could also write a 3-level state as sine theta, cosine phi, sine theta, sine phi, cosine theta, and then with some phases here, phi 1, phi 2, something like this. As long as you have all possible combinations here, okay? But if you do it this way, and then if you try to calculate the Berry curvature, for example, or other quantities, you could find some formulas, but things don't decouple. Why is that? Because, so here, what I'm doing here is actually that, like, if you look at the Gell-Mann matrices, there is some certain symmetry coming from the algebra. So I have some sigma z lambda 3 block. So the first 3 Gell-Mann matrices, 1, 2, 3, there is some diagonal elements, and then these ones corresponds to mixing within that element. And then with this block, and then with the last element, these all lambda 4 to 7 correspond to mixings between that block. So I'm distributing these angles by respecting this symmetry. So, and if I do this thing, I see that Berry curvature nicely couples, and this was already something that like I was expecting, because that was, I mean, the motivation comes from these diagonal Gell-Mann matrices. So what I'm trying to do here is that, so in 2-level system, I have sigma z operator that I usually assign to the north and south poles, right? But there's nothing special about sigma z. I might just as well use sigma x, right, as my north and pole. But 2-level states are nicely symmetric, and then simple enough. Even if I say that, oh, I'm going to stick with sigma x now, spin x, everything just like algebra works nicely. But 3-level systems, and then from there on, it's too complicated. If I don't respect this symmetry of the algebra, things don't decouple. So the structure is still there, but it's just too complicated that you cannot see. And when I see these Jacobians, it means that, so I have a Jacobian, so this is the cosine theta, which is given by some lambda 8 vector. These factors here, they don't matter. They come because this lambda 8 here has this 1/√3 there. Sigma 3 doesn't have it, so it comes directly. So, but it has some z-axis character. It changes between +1 and -1. So I define some vector with its position along the z-axis and then its azimuthal angle. That defines a sphere. Okay, so so if I do this thing, I get these exterior and interior spheres that I call. And another way that, like, if I just like look at the Berry connection, for example, if I write the Berry connection for this state and then Berry curvature, I get a Berry connection is given by the gradient of these azimuthal angles. And then I need to take curl of it to find the Berry curvature number. So normally you would say that curl of a gradient is 0, right? Unless this phi has a singularity in it, discontinuity, then you need to include the winding. And to have this Chern number non-zero, when I take the curl of it, so this guy and this guy must be actually singular. This tells me that I need to be at the poles, because those were the places that like that the azimuthal angle can become singular only. So what's happening is that, so I have again my two-dimensional brilliant zone. So now let me choose some some reference point, this point in momentum space. And then if I'm interested in the Chern number of the lowest band, doesn't matter, this applies to any band. But let me take the eigenstate at this point, 1, 2, 3, okay? At any point in the brilliant zone, any other k, I'm gonna express this in the basis of these eigenstates by using this parameterization I showed. So at this point, in this basis, this eigenstate is 0, 0, 1, right? I'm completely in the 1 basis. When I go a little bit around it, so in the exterior sphere, so this is going to point to some other directions, but again, I can find a continuous smooth transformation to rotate this back to the South Pole, unless at some point I flipped. Then I don't have a continuous transformation. I don't have a rotation defined, a unitary transformation defined. So it means that my Chern number changed. So to have some non-zero Chern number in a multi-level state, you must flip on the exterior sphere. After flipping on the exterior sphere, your theta becomes 0. Here, if theta becomes 0, so this cosine square is 1. And depending on cosine var phi, if this is pi or 0 or pi, so you can be at the north and south pole of it. So that's why they are nested. And here, if this is plus and minus 1, there can be also a singularity here if you're also on the north pole of the interior sphere. So what this tells you that there is some nested structure coming from the algebra. And if you're interested in topology, Chern number, this can be represented as the coverings of each sphere. But the exterior one is special because that's the largest one. And then you must flip on that one. The other ones come only as a topping up to this exterior structure. Okay, so that's why I like calling this one sphere to rule them all for Chern numbers. So, and this structure is actually completely generic. So if you go to an n-level system, now you have generalized Gell-Mann matrices, and I'm focusing on the diagonal Gell-Mann matrices. So Gell-Mann matrices, the SUN generators must be traceless. So how many traceless diagonal matrices you can write in n dimension, okay? So what you can do is that put 1, 1, 1, 1 here and minus and minus 1, traceless. So I treat this one and this block as a two-level system, and the azimuthal angle is gonna correspond to mixing between them on the pole. And if I zoom in here, I can write 1, 1, 1, 2 minus n. So again, this thing is a two-level sphere, all the way down to the sigma z that I'm familiar with, 1 minus 1. That's again a two-level system. So what's happening is that for an n-level system, you need in general, so this is some wave function, n by 1. So you need n complex numbers, 2n real numbers, but there must be normalized. Overall phase doesn't matter. So you need 2n minus 2 parameters to characterize this CPn minus 1 projective plane, complex projective plane. And to define a sphere, you need two things. One z-axis value, polar angle, and one azimuthal. So these corresponds to n-1 spheres, which are the diagonal Gelman matrices present in the algebra. So what I'm, for 4-level system, for example, I have a 2-level description. I take it and embed it in another 2-level description, take this and embed it another 2-level description, and it goes up. So in another way, when I have a 4-level or 5-level system, and then if I'm interested in this one, what's happening in this guys doesn't matter. So I can just see them as degenerate. When I zoom in this manifold, again, there's another 2-level structure. Or in another way, when I have like these many states, I can just like take these ones and push everything out. So this tells you that to have a topological transition, you must have a band flipping. Bands must invert, and then this must happen in the exterior sphere. And to understand this bulk-edge correspondence, what you can think about is that when you interface some system with vacuum, okay, so for example, imagine that I have A and B atoms flying around vacuum, completely trivial. If I capture these A and B atoms and then force them into a lattice formation, but this is deep lattice, so no tunneling and something, and then let me imagine that I arrange them in a honeycomb pattern, okay, so I have two bands. So they don't talk, bands are going to be completely flat, okay? So each band is going to have only one linear character. So linear centers are completely localized. So these are for the lowest band is A, upper band is B. I can start deforming this system. That's okay. But this is still A only. This is still B only. At any point, if I want to have churn number 1, I must invert these bands. So this color must change. And this is irrelevant to what's happening, whether I have any bands above or below or not. Okay, so I must invert. So for this band, if I have pink color, so one sublattice character, I must have the other character. So if this is something called like pink is, for example, 1, 0, 0, 0, okay, in this basis, so I must have something 0 here and anything here, that it is orthonormal. And if I take some finite system, so now let me imagine that I have this thing that I just like change the topology in the lattice, and then I have a finite system, okay? So some edge with the vacuum. So vacuum is characterized by this thing. You can think about it atomic limits, okay? The things are not talking. So right at the interface, to connect this yellow to the B here, there must be a chiral edge there. And then this one must connect to here, directly at the edge, because I'm interfacing with the vacuum. And this is what dictates me that if your churn number is 1, so you must have these edge states at the edge of the system, okay? So this is the bulk edge correspondence. And if I just like take these ideas and then put this in context. So what I have is that so for 3-level system, for example, I can imagine Hofstadter. How many minutes do I have? This one? Okay, cool. So if I take the Hofstadter model, for example, if I take a square lattice, and then if I put 1/3 flux, so I have 2π/3 flux here. Then if I just like go around it, this model has 3 bands. And then if I just like look at the exterior sphere distribution on the exterior sphere, starting from one reference point, for example, I start from here. This is the azimuthal angle on the exterior sphere. It must flip, and it is actually flipping at 3 points because this lowest band has churn number 1, and all it reduces to actually windings around these points. So this is one way of just like seeing things geometrically, but also beyond topology. So these geometric ideas can be quite useful. So in the spin orbit microlasers, for example, in the more quantum computation ideas. So one way, so you have qubits, and then everyone is trying to get many number of qubits that are coherent, right? So that is one way to go. Another way is actually, instead of trying to add more qubits, you can think about adding more internal degrees, extending the dimension of your Hilbert space, okay? Instead of qubits, you can have qubits to increase the computational capacity of your system. And this increases the the circuit complexity a lot. But even for 4-level qubits, for example, you can prepare it. They could prepare it experimentally. But until this paper, for example, can you prepare any qubit, 4-level qubit state, and then can you do operations on it? This was not possible because there are too many degrees of freedom, and then how are you going to show it? So for 4-level system, you can see this thing as 3, because I said like n-1, 2 spheres. You can see this thing as 3 2 spheres, and then by expressing this way and then preparing the states on these more blocks, 2-level block spheres that I'm comfortable with, they could actually show that that they can prepare any 4-level qubit states and generalize SU4 algebra. So these geometric ideas can be useful. But so with this, so now I have these, so everything I told you here is a single gap topology. And then I'm still talking about single gap topology, but now I want to go out of equilibrium. If I have a Floquet system, okay, so I told you about these edge states and then periodic driving. And when I have a time-dependent Hamiltonian, all these descriptions we know of tenfold waves, crystalline symmetries, when I have Floquet system, this is lost. So everything had to be extended. Why? Because if when my Hamiltonian is periodic, so I have this 2-dimensional system, for example, imagine that I take this one and I'm shaking it, or I shine some laser on it with circularly polarized light. Hamiltonian becomes time periodic, and this laser is constantly pumping energy to my system. So I cannot talk about energies. What I can talk about is a quasi-energy, as you're familiar with. So, and because the time evolution operator is the important thing, it's defined as the phases of the eigenvalues of this time evolution operator at the end of one period. And because these are phases, they can only be defined modulo 2 pi. So it means that if I have 2-band systems, I'm going to have infinitely many replicas of it. Okay, so, and the reason that like I lose this bulkhead correspondence is that I have this 2-level system. I can define this thing in different ways. I can induce, I told you, topology can change through band touchings only, and then these can happen in this gap, which is the anomalous gap, or in the regular 0 gap that I'm comfortable, I'm more used to it. So what I'm saying is that, so when I have 2 bands, Chern number 0, everything is trivial, I can induce some band inversion here, which are, and they're gonna, it's gonna leave some edge states behind. So I change the Chern number from 0 to 1, but now there is some edge state here, which I'm counting as 1. But then instead of doing a band inversion here, I can also, because this one has its replica, Floquet replica, I can also do a band inversion between its Floquet replica. This will also change the Chern number 1. So now what's interesting and what was unique to this Floquet system is that if I do a band inversion after this one also here, so this will from here to here, this will set the Chern number 1 back to 0, but because a band inversion here cannot annihilate the edge states here, so it just introduced new set of edge states here. So now I have edge states in the system, but I have Chern number 0. And this is something completely unknown. And so that's why these anomalous Floquet topologies have been attracting a lot of attention. And so Chern number is given by this 2-dimensional integral. So now for the topological invariant, this is insufficient. I need to write a 3-dimensional integral, b squared k, on the 2-dimensional billions on torus, but time is also periodic. I need to include it. And then it's given by the derivatives of the time evolution operator, ugly looking thing. Okay. So, and while Chern number has been also, Berry curvature has been directly measured also in solid state context, but also in optical lattices by using several different methods, observing this thing hasn't been done directly, this formula, because you're trying to treat the time evolution operator. And I'm telling you that you need to take time derivatives, integrate it, also position that, what is this, right? This is not accessible in this form. So, but, so there's this beast of a winding number, and then how to measure it is the problem. Our approach was to look at this winding number from a different way, okay? In terms of topological band singularities. So just in terms of, instead of focusing the time evolution within the period, we can also do that. But we know that topology changes through band touching points, right? And this is like how I'm just like transferring charges, topological charges between bands. Why not? Why don't I just like look at those things and then just like keep track of it? So this was the idea, and then this has been implemented in an experiment in Munich beautifully. So what's happening is that we first go to the high frequency regime. So in the high frequency regime, so what I have is that I have these two bands, but its Floquet replicas are well separated, right? If they're well separated, they don't talk. If they don't talk, so nothing is happening in this gap. And so we established this high frequency regime is equivalent to the equilibrium characterization. So there are Chern numbers. We know how to treat Chern numbers. They can be measured, all good, because nothing can happen in this gap. If anything is happening in this gap, it must be given by the Chern number. Okay? And from that point on, we parameterize the Hamiltonian by some parameters that we are changing, and then we change the drive. We go to our target Hamiltonian, Floquet Hamiltonian, with the parameters that we want. This could be, for example, this is starting from the high frequency regime, which is really high frequency laser. We are gradually decreasing the frequency to go to our target thing. In the meantime, you can induce sublattice potentials. You can also increase amplitude, whatever you do, so you can just dump into this lambda. In this parameter space from high frequency to low frequency that you want to go, you will go through some topological transitions. So these different lobes, but at every point, at every crossing, you can just like come from anywhere. So you will have these band singularities happening between the gaps. So the idea is that, so now I just like look at the width of these bands from the high frequency that I started, and then all the parameters that I'm tuning, so bands get more dispersive, they spread, and then they start talking, exchanging, talking, and then at some point they can change their, did I? Okay, so because at each point, it just like goes through topological singularities. So the idea is to detect these singularities and then measure their topological charges. And then at the end, you just need to sum them in a gap specific way. Okay, so what's happening is that mathematically, so this is at any band touching point, this is a Dirac cone, two-dimensional. But when I'm tuning the parameters, so bands are coming, touching and reopening. So this is actually a three-dimensional while mode happening there, three-dimensional touching. So mathematically, its charge is given by how the Hamiltonian generating these bands are wrapping around the Bloch sphere. You can think about this thing is that this is a topological singularity. If I just like put it in an enclosed surface, the flux coming out of it must be quantized. Okay, so this monopole, so experimentally how this was done is that, so this is the kx ky plane. So at the bottom and top of it, I have the Berry curvatures, and then the walls are the z-axis is the parameter that I'm changing. If I just like now increase this thing really flat, the sides are not going to matter. So I have some flux coming in and then some flux coming out of the thing. And then this can be measured in experiment. Right before the topological singularity, you have some Berry curvature distribution. Red and blue are plus and minus. So band touching is happening here. And then after it, it just flips to it changes its sign. And then if you just like measure the amount of this charge that has been accumulated here, this gives you the charge of and this is extremely quantized because essentially this is given by the sign of the determinant. So you're going to get plus 1 only here. So, but one crucial thing is that experimentally, so you have a Floquet system, but whatever the probe that you're implementing in solid state, in optical lattices, so if you want to get the gap out of it, you have two bands here and their replica. What you can measure is the minimum gap only. Okay, when you're at the high frequency regime at any k point, so these are well separated, you are measuring the zero gap because that's the smallest one. Okay, and then here that's what's happening. So experimentally here this was a graphene, so implemented by having some honeycomb model and then by tuning the tunneling parameters in a cyclic way. If you want, I can tell more details. But here what we are actually tracing is the gamma point and then the gap value at the gamma point, okay, coming from the high frequency regime. So at the high frequency regime, these are two bands. These are much more separated, and I'm detecting this gap here. And then at this point, I have the Chern number classification that I can measure. I'm labeling the winding numbers in the 0 gap and pi gap. So it's 1, 0. Nothing is happening in the pi gap. So as I decrease my frequency, this gap is starting opening. So I have two bands. Oh, now they start coming closer, and then they want to talk. At some point, when they are equal, and then they are going to change identity. Instead of 0 gap being the smallest gap, pi gap is going to start being the smallest gap. So I'm going to start detecting that one. So it was initially increasing, and then suddenly the gap I'm going to measure is going to start decreasing. And this gap labeling is crucial to identify which gap you're probing in the experiment. And then here in the experimental data, it can be seen very clearly. There's a kick. It indicates the gap label change. So now you're measuring the pi gap, because now that's the smallest one. And then at some point it closes. It means that you have an anomalous gap closing, a clear evidence in the experiment that you detected. And then its charge can be detected by measuring this topological singularities, proving that we are in the anomalous Floquet regime. So but this doesn't stop there, because one experimental capability that's being developed in the experiment is that now with the quantum gas microscopes and then tweezer arrays, so people are getting much more control individually in the system, and then you can have sharp edges. So now imagine that you have these different systems, you have edge states. So these states you can have in the equilibrium too. This one is unique to out of equilibrium, truly out of equilibrium phase. You have edge states. One question you can ask is that, are these edge states any different than these ones in the quasi-energy perspective? Or the topological transport in this one, is it any different than these ones that you can get in the equilibrium? And experimentally, this is within reach, but you can, because people can do sharp edges now and then induce wave packets there to probe these edges with respect to each other. And then this is what we looked at in another paper. And then by using different drives, so we have this 1-1, we have edge states in both gaps, but we also identified an mostly overlooked phase, which has -1-1. So you can have edge states there, but they can also have different chiralities supported by the same band. Even Chern number is 2. If you look at the edge transport, if you just like induce some wave packet there, you see that in the 1-1 phase, they have same chirality for the 0 gap and then the pi gap states. But in -1-1 they have the opposite chirality. And then they really don't hybridize the pi gaps and then the 0 gaps. They just like go through each other because they are energetically well separated. What's interesting is that, so I take a finite system and then I induce some wave packet, and then I look at how it just like moves along the edge. So if I have this anomalous edge state, that I have edge states present in both gaps, they are both going to contribute. They might, unless they are well separated in momentum. So this is the edge transport, like how much was the probabilities moving along the edge as a function of time on the edge sides. And then this is the Chern phases, like Haldane phases, that I have edge states only in one of the gaps. I mean, this is the same energy scale and it's not that visible, but there is more red here. So there are more of the probabilities flowing in the edge. And this is very surprising, because this tells you that this thing can be more robust. Robust in the sense that when you initialize the system, they are easier to trigger, and then they are going to give you more edge states. And if we do this thing actually as a function of different cuts on the phase diagram, so these are the probabilities, that how much of the probability is going to the edge states of your wave packet. So it can be like, this is in the anomalous phase with respect to the Chern phase, it is almost close to the 60% summing both phases, as opposed to the 20 here. And then this is with respect to this phase. So it actually tells you that if you are in a Floquet regime, in an anomalous Floquet phase, it could be easier to probe and then get more robust transport out of these things. And this has been also experimentally confirmed. So they could actually study this 1-1 phase And experimentally, -1 one is not possible yet, I believe, but it still gives more robust transport in that sense. So more edge states are good in terms of edge transport. That's the merit. So with this, in the remaining a few minutes, I want to give you a teaser for what's going to come tomorrow. So everything I talked here is single gap topology, all the tenfold way, K-theory classifications, what we know, so they are single gap topology. What this means is that I have a Fermi level lying in some gap, or in Floquet system, I'm interested in some gap, and the topological characterization of the system correlates with changes happening in that gap only. And then you can treat different gaps and sum all of it. So everything we know is single gap topology. So, but now in the last, so the first proposals go back to 2020, in the last couple of years, there's these multi-gap topologies have been arising. And now what's happening here is that I have, so I told you for Chern number, you need minimum 2 bands because you need minimum 1 gap for something to happen there. So for this, I need minimum 3 bands. And then the topological protection in this system is gonna, so it correlates with things happening between this gap, and then how they just like wind between each other. So that's why it's completely different, falls out of all the non classification. So I can have 3 bands and then some while nodes, some singularities here, Dirac cones, and then topological charges of these Dirac cones are given by the non-abelian Berry curvature now, or these 2 eigenstates, how they wind around each other. And most interestingly, these band nodes in between different gaps to induce this non-trivial topology, they must be braided. So they have non-abelian braiding properties. So, I mean, fractional quantum Hall states are interesting. I mean, we like them, they are interacting, and then it can be harder to treat or just like experimental observe. So here, this is completely single gap. And I'm talking about some non-abelian properties happening within the Hamiltonian subspace. So if I have 2 band nodes here in the gap 1, so it's not a gap anymore, but I'm just like referring to the submanifold of 1 and 2, band 1 and 2, and I can have some band singularities. They are going to have minus and plus charge because that's how I created them out of vacuum. So I just like separated 2 Dirac cones, and I can have another Dirac cone here. And if I take this one and this one, and then by modifying the Hamiltonian, if I braid this one around the band nodes in different gaps, if I braid them around, normally they were, before they were annihilating each other. They had plus minus charge, so they annihilate. But after braiding, their charges flip. So now they cannot annihilate. I have band nodes here with the same charge. And Euler class measures exactly this. It measures obstruction against annihilation of the band nodes that comes about through these non-abelian braiding. And it is in a way a fragile topology because you can just like induce band nodes from here to annihilate that thing. But concrete experimental signatures of how to measure this braiding, how you're gonna just, what are even the bulk edge correspondence for this thing has not been completely established yet. So concrete experimental signatures are quite interesting and an active question. So I will first give you an intuitive way of just like how this braiding works. And then I want to show you 2 different, like under periodic driving and quenches, how this Euler class observables can be observed. But with this, it will require a little bit of background covering of quaternions. So with that, let me leave this for tomorrow and conclude. Yeah, I hope I could just like convince you that like these geometric way of looking at the topological invariants, I mean, topological invariants are interesting, but the protection really comes from this deformation in the Hilbert space. So I talked to a lot of mathematicians, and then, I mean, they know topology much more than I do, certainly. And then, but the first thing is that, which is very natural for us, right? I have a Fermi space, a Fermi surface, I have this eigenstates that I'm dealing with. it is hard to cover in a sense that it's just like, what is the vector bundle? Is it the projected one? What is it? What are we looking at? What is the topology? And this is very interesting from also mathematical point of view of a mathematician. So all these geometric ideas, how I can deform the Hilbert spaces of the Hamiltonian, is very useful. And then if I go to the periodically driven systems, I have new invariants like winding numbers that I can observe, and then actually experimentally relevant. But this will extend to more Euler class and quench dynamics and linking numbers tomorrow. So with that, thank you.
Okay, thanks, Ünal, for the fantastic introduction. We'll open it up for questions.
Sorry for running a little bit over time.
Just raise your hand and I'll bring the mic around.
I was just kind of curious if I'm going through like a topological transition and the Chern number is no longer quantized or 2 bands. How do I think about this for the 3? Do they come a touching point of 3 bands?
Exactly. So, oh, you mean all 3 of them?
All 3 of them are touching at the transition?
Yes, you can also have triple degeneracies happening, but in the band topologies, to have triple degeneracies, you must have some external symmetry that's actually forcing you to that. If you have C6 symmetry in your lattice, for example, or just like some other symmetries. So, because what's happening is that the math is same. These changes in the single gap topology, it must go through the band touchings between these ones or these ones, whichever ones, but you can have at the same time happening at different gaps, like in gap 1 and gap 2 at different momentas. They could be also happening at the same momenta that all 3 bands touch at the same point, but this requires additional symmetries in the system. Math is same, but yeah. Is that what?
Yeah, so in the case where they don't happen at the same point, whether like those are 2 transitions or are they happening at like the same value of the Hamiltonian? I don't know if my question's that clear.
It depends. You can also induce them at the 2 different points. That can also happen. But in terms of Chern number, how it changes, you can just like track them one by one.
I see.
If they're like happening and then opening, like at some point and opening. What you can do is that you can consider the first band first, and then, oh, like what is this guy's charge? How much it changed? This is this one's Chern number. And then consider the second one. Oh, it changed here, but it also changed there. Consider that one standalone. And then if your Fermi energy is lying in the second gap, you just like sum the Chern number of first one and second one. So you can track them in a single gap way. Exactly. But they can also happen simultaneously.
This is working. I had a quick question about the representation of 3-level systems at the beginning. So with 2-level systems, I think of all the states as basically equivalent because I can rotate one to another. And with 3-level systems, I guess that uses up 2 of the 4 parameters. And then the other 2 of the 4 parameters must be kind of ways that different 3-level systems are sort of intrinsically different aside from a rotation. And I guess I could see, I'm wondering if your representation gives sort of an intuitive picture for what those 2 parameters are. Like I imagine one is sort of the difference between a vector state and like an axial state. But I wasn't sure if there's a neat way in these nice variables to think about sort of what are the ways that a spin 1 or 3-level system state can be physically different from another, aside from a rotation.
Yes, so it's actually, so yes, and this geometric way of looking at things, it can be also tailored for specific, like, so if you have a 3-level system, and then for some reason, oh yeah, maybe also this one. So if you have a 3-level system, so the parameterization I showed you, this is the most generic way that like entire SU3 that you can cover. So, but you could also have some subset that you're interested in. Spin ones are, subset, they don't cover the entire thing. So depending on how we are distributing these variables here, with this one, for example, you could target just like, for example, if you have a 2-level subspace, this could be this one and this block. One way if that you are accessing it, but if you're interested in some other properties, maybe how they wind around, you can also choose them differently. But my point is that it's in a way just like trying to respect how the algebra lays out. And then if you have, for example, within this subspace, you have some correlations here or there, and then I want to put the phase difference there, just like thinking that kind of logic, which sphere you're targeting. So that simplifies the algebra a lot. Also in the four level case, for example, for the four level qubit. So some qubits has been demonstrated, but they were practically qubits, like 2-level subspace of it. So in a way that like there is some big sphere, and then you are accessing, like treating this one and this one as a chunk, which is practically a two-level state. And then that has been the only possibility up until now. But if you're interested in also some couplings within that, you could introduce it by using these angles and then this axial azimuthal angles, for example. Yeah.
Okay, if there's no more questions, let's thank Ünal again.
Thank you.